In this video, we discuss variables and scales of measurement. In previous videos, we've talked about data and variables in samples and populations. Let's take a few minutes to discuss different ways that we can conceptualize or classify variables. First, let's look at exactly what we mean by the very idea of something being a variable. A variable is a characteristic or feature for someone or something that, you guessed it, varies. Different variables may vary in different ways. For example, it may vary over time. Something like height in children varies over time as children grow taller. Reading ability or science knowledge varies over time as children learn more. Depression levels vary, getting better or worse over time. Now, another way that a variable may vary is to stay the same within a person, but vary from person to person. For example, a person's race or ethnicity doesn't change over time, but it does vary person to person. Another way that things may vary is place to place. Something like neighborhood environments may vary based on crime, resources, or community support. From the practical perspective of what does this mean for my study? Just because something can vary over space or time or person to person, it doesn't automatically make it a variable in our study. You can have data from a small school in Maine or Alabama where all of the students are either white, non-Hispanic, or African American. In those cases, race ethnicity is not a variable. It's what's called a constant. It doesn't change, at least not in our sample. From a research perspective, we'll see that there's really not much you can do with constants. You can't examine whether girls study more than boys if all of your data come from an all-girls school. Now, there's several ways we can describe or categorize variables. One approach is based on the fundamental role that the variable plays in our research study. Is it a predictor or is it an outcome? Predictor variables are variables that we believe influence other variables in some way. Because it has an influence on other variables, we can use it to predict values for those variables, hence the name. For example, if I'm interested in understanding children's reading ability, I might use parent education as a predictor variable. I believe that the level of parent education will have an impact on children's reading ability, and knowing parent education will help me predict and understand why some children have stronger reading skills than others. Predictor variables are also often called independent variables, but technically, independent variables are a very specific type of predictor variable. An independent variable is a predictor variable in a true experimental study where the level of the predictor is being manipulated in some way by the researcher. For example, let's say that I'm interested in studying the relationship between the amount of math homework a student receives and his or her performance on a subsequent math test. I can make this a true experiment by randomly assigning some students 20 homework problems, other students 40 homework problems, and others 60 homework problems. In this case, it would be completely appropriate to refer to amount of homework as an independent variable. In contrast to predictor variables, an outcome variable is the variable that's being influenced or predicted by the predictor variable. Returning to our initial example, if we think that parent education predicts children's reading ability, then children's reading ability is our outcome. Outcome variables are also often called dependent variables, but as with predictors and independent variables, dependent variables are a very specific type of outcome variable, and technically the term only applies to outcome variables in a true experimental study where the level of the predictor was manipulated by the researcher. Returning to our example where we randomly assign students to 20, 40, or 60 homework problems to see if the amount of homework they did predicted performance on a test, scores on that test can correctly also be called a dependent variable because the different levels of amount of homework was set by the research team. But again, people often use the terms predictor and independent variable interchangeably, as well as outcome and dependent variable. So don't get shocked or confused if you end up reading someone talking about an independent or a dependent variable when they're talking about a non-experimental research study. Now, another way of conceptualizing variables is based on whether they're continuous or discrete. This applies to both predictors and outcomes and comes down to the range of values a variable can take. A continuous variable can take any possible value within some range. Now, the easiest way, I think, for determining whether a variable is continuous or not is to ask yourself whether you can infinitely refine a measurement going into smaller and smaller decimal places. You might never want to, but theoretically, could you? For example, the length of someone's foot in inches is continuous because you could, with a detailed enough instrument, measure a foot that is 6.538746843 on and on and on inches long. Again, you're never going to do that. You'll round at some point. But theoretically, the construct of length of a foot is continuous. Other things that are continuous include height, weight, and age. In contrast, a discrete variable only assumes set specific values. For example, the number of people in a diner is discrete. You can't have 2/3 of a person eating in a diner. There's a zombie joke in there somewhere, but let's not go there. The number of cats someone owns is also discrete. Someone may have a lot of cats, but it's always a whole number. I won't say it. That said, a discrete variable can have fractional values. The key is that it's a limited number of fractional values. For example, shoe size is discrete even though you can have 8.5, 9.5, 10.5 size shoes. But notice, shoe size is not continuous because you can't walk in and ask for a size 10.9482052 Nike. Now, as I implied earlier, continuous variables may be rounded into discrete units when we measure and report them. We don't measure height to trillionths of a millimeter. We round at some point. But assuming you haven't rounded so much that there's only a couple of values left, for example, rounding the height of children to the nearest meter, we still treat it as a continuous variable. Now, another way of conceptualizing variables is based on their scale of measurement. A variable's scale of measurement reflects the inherent type of information that's contained in that variable. To understand and remember your scales of measurement, it may help to think about Humphrey Bogart.
Give them Cairo. Well, by guess.
And suppose we give them you, Miss O'Shaughnessy. How about that, huh?
You want the Falcon, I've got it. The Fall Guy's part of the price, I'm asking. As for Mrs.
That's from The Maltese Falcon, one of the early movies from the classic film noir period in Hollywood. And noir, N-O-I-R, is also an acronym for the 4 different scales of measurement. in order of their strength and flexibility: nominal, ordinal, interval, and ratio. At the most basic level of measurement, we have the nominal scale. This consists of categorical data, things like race, ethnicity, date of birth. They're names. You can think names nominal. Now, categorical variables vary in kind rather than in degree. You can think of it this way. There's no natural ordering of states. Wisconsin, California, Maine, or Hawaii are categorical. Now, there may be an ordering for characteristics of states, their population size, the year the state entered the Union, but simply the state itself has no natural ordering. Now, you'll also notice that people may assign numeric values to different categories, but again, these are just arbitrary and have no meaning. For example, the registrar's office may have codes for a student's major, with 1 for psychology majors, 2 for education majors, 3 for biology majors. But that doesn't mean that biology majors are somehow more than psych majors, with education majors somewhere in between. You can't combine the values or add them up in any way. If a psych student 1 and an education student 2 had a baby, it wouldn't be a biologist 3. Okay? Now, you'll also notice that some texts, including texts I've used, will use the phrase qualitative data and nominal data synonymously. But I gotta be honest with you, I am not a fan of that. We have a term for nominal data. It's nominal data. We don't need to use qualitative data as a synonym. It just muddies the water in regards to the distinction between quantitative research and qualitative research, and quantitative data and qualitative data. For example, you can have qualitative data, observations of children's behavior on a playground. Code those observations based on how many seconds of cooperative play a child performs with others, and analyze that qualitative data quantitatively in a statistical analysis. Many students and professors lose sight of that, and it drives me crazy. This point is so important. I want to repeat it one more time in a way that you'll hopefully never forget. So I'm going to use my hamster voice. You can take qualitative data, code it quantitatively, and analyze it in a statistical model. Okay, hopefully you will not forget. The next scale of measurement is ordinal data. Ordinal data has, you guessed it, a natural order to the values. Higher values come after lower values. But, and this is key here, there is no inherent equal spacing between values on an ordinal scale. The values aren't equally spaced. I think the most clear example of an ordinal scale is rankings, or the place that someone comes in during a race. If you're looking at someone's place in a race, the numbers 1, 2, and 3 tell you the order, but say nothing about the actual distance or magnitude of the difference between those values. First place may come in well ahead of everyone else, while the difference between second and third is only tiny. In behavioral research, one of the most popular ways we have for measuring abstract constructs is through the use of Likert scales, named after this guy, Rensis Likert. Likert scales are ordinal scales, And yes, to answer one of those burning questions researchers often have, it's pronounced Likert, not Likert. Likert scales are 5-point scales ranging from strongly agree to strongly disagree. Hopefully you can agree that while there is an order to the values, 1 reflects stronger agreement than 2, which reflects stronger agreement than 3. The actual difference in the magnitude of agreement is not equally spaced. Is the difference in agreement between strongly agree and agree the same as the difference between undecided and disagree? There's no reason to think so, and to be honest, I really doubt it. The next step up is an interval scale. Like an ordinal scale, with an interval scale there is an inherent order to the values, but the spacing between the units on the scale are now equal. I think one of the clearest examples of this is temperature on the Celsius scale. Each 1 degree increase is exactly the same amount of extra heat as the previous 1 degree increase and the next 1 degree increase. The difference between 51 and 52 degrees is the same as the difference between 61 and 62 degrees, or 1061 and 1062 degrees. Now I'm going to ask you a question and I want you to answer as quickly as possible. Don't think about it. Is 100 degrees Celsius twice as hot as 50 degrees Celsius? No. And if you got it wrong, it may help to look at a thermometer. Notice that when we measure temperature in Celsius, things can get a lot colder than 0. The scale has an arbitrarily set value of 0. Yes, I know it's not arbitrary in the sense that there's a basis for 0 being the point where water freezes. But it's arbitrary in the sense that it's something that doesn't have a true or absolute 0. The key is that 0 is not the lowest possible value. You can get values well below 0. And because of that, 100 degrees is not twice as hot as 50 degrees because there's still 273.15 degrees below 0 that you can go down to before you reach absolute 0. In contrast, the final scale of measurement, a ratio scale, has all the strengths of an interval scale. There's an inherent order to the values that are all equally spaced, but a ratio scale also has a true or absolute 0. Because of this, if one score on a ratio scale has a value twice as large as some other score, it really is twice as big. Examples of ratio scales include distance and height. 10 miles is twice as far as 5 miles because you can't physically measure negative miles. 6 feet is twice as tall as 3 feet because you can't have a negative height. In temperature, it's the Kelvin scale, where absolute 0 is 0 and you can't get any colder, period. In the end, the measurement scale you have determines how you analyze your data as well as how you discuss it and present it. There are whole classes of analyses for nominal data and other groups of analyses that require at least an ordinal scale. A lot of what we're going to focus on requires interval or ratio data. So being able to recognize the scale of measurement in your data is vital to doing analyses correctly. Okay? That wraps up this video. So we'll see you later. Bye for now.